In this video, we're going to be looking at position versus time graphs, and we're going to be defining what is the velocity, how do we get the velocity from this kind of graph, and what is the difference between average velocity and instantaneous velocity. Earlier in our first video, we talked about motion diagrams, which were really helpful in visualizing the motion of an object. For example, we have a student standing still here, going at the same speed, speeding up here, and slowing down. But there is another way to visualize that, and that's with graphs. Imagine we have a dragster that's speeding up down this track, and we can look at this with a motion diagram and say this is where it starts off at, say, position A. But the problem is we will only get sort of certain points in time and its position at each of those places in velocity. We might put, say, this point here, this is like at 2 seconds. Or at 3 seconds would be, say, maybe over here or something. And then at 4 seconds would be way over there. So this is point B. These points would only be just telling you what the position was and the velocity and at that particular point in time. Whereas a graph gives you a continuous picture. It's plotting a graph of the position over time. It's a function. It's the position as a function of time. In the graph, along the y-axis, we're plotting the position. So the rise is like the displacement. And on the x-axis, we're plotting the time. So the run is like the time interval. If you were to take two particular points in time, like A and B, and you knew where its position was, this would be the position, say, x of 1, and then B would be at a position of x of 2, with respect to the origin here, then the difference between these two positions would give you the displacement, which we could represent with a delta x, or is the rise in the graph. And if you divide that by the run, which is the time interval, you get the average velocity. So the big idea here is that if you take the slope between 2 points on that curve, you get the average velocity. This is a very important point. And so you should remember that the slope of a position time graph always gives you average velocity. But would that tell you what your velocity was at A? Or what your velocity was at exactly at 2 seconds? Or at 3 seconds? Or at 4 seconds? No, that's actually just telling you the average velocity between this particular point in time to this particular point. It's the average velocity between that time interval. In fact, in this particular picture, the average velocity over that time interval is not the velocity at A, because it's going pretty slow there, and it's not the velocity at B, because it's going really fast there. It's the average velocity. It would only be the same as the velocity at A and B if the object's motion was uniform and it was not changing at all. For example, in this graph here, the average velocity over this time interval wouldn't be changing at all because it's a straight line. So I guess if you go back to this problem, the average velocity isn't probably the most precise way of telling you how fast that object is moving at A or B because they're different speeds. So we need to talk about something called instantaneous velocity. So average velocity is velocity over that time interval. But what is the instantaneous velocity? Meaning, well, how fast is the dragster going at A? Or right here at 2 seconds? Or right here at 3 seconds? Or right here at 4 seconds? You know, if you were to look down at that speedometer and see how fast it's going right at that point in time, right, that would be called the instantaneous velocity. It's the velocity at that instant in time. Okay, let's go to the next page of your notes. So the instantaneous velocity is the velocity at that very instant in time. You see, average velocity is the slope between point A and B, and it's not the instantaneous velocity at, say, t1. But if we were to kind of shorten the time interval and move this point B closer and closer and closer and closer to t1, we'll eventually get to one point on this curve. Take a look at this picture over here. There's the function right in here, and this blue line that I've drawn is what we call a tangent line. And the slope of this line, this rise over run, would give you the instantaneous velocity for that particular point in time. This line is called a tangent line. you could think of it as we're trying to find the instantaneous velocity at this particular point, t1. We're going to move b really close to it, right beside it, so close, infinitesimally small. So this little tiny triangle that I would draw here has a very tiny time interval. The instantaneous velocity at this particular point time t sub 1 is the average velocity over this tiny time interval delta t centered right along at that point t1. In calculus, this is really called the derivative of the x function. If you're in calculus, you would learn something called dx by dt at some point. Anyway, this is not about calculus-based course, but that's where the definition comes from. So what do you need to know in this algebra-based course? You need to think of instantaneous velocity as the slope of the tangent line to that curve at that particular point on the position time graph. Now, that's a tangent line, and a tangent line only touches the curve at one point. So if I give you a graph like this, you should be able to look at the graph and be able to tell me some things about it. For example, if I pick this point A right here, and then another point here B, and then say another point here C, you should be able to tell me some information about it. Obviously, we could talk about the position of where it is. Like A is below. This is, let's say, 0, so it's below. It's behind the origin. It's a negative value. And B is at the origin, and C is in the positive direction from the origin. But let's talk about the velocity. So if we were to talk about the instantaneous velocity, what we would do is then draw tangent lines at each of those points. For example, at A here, we could see the slope here is 0. Means that it's not moving at here at A. And also over here at C, it's a 0 slope. So the object is not moving. Where if we look at B, we can see that's a very steep line here, and you're getting a maximum velocity in the positive direction. But if you look here, that's a negative velocity because you have a negative slope. Over here, that's the negative velocity here. This is all kind of shown down below as well. So when the slope is positive, that means the object's moving in the positive direction. It's moving forwards. And here, when the slope is very steep, you also have a positive velocity, but it probably is a maximum positive velocity. This is 0 velocity because it's 0 slope, and now you have negative velocity, and here it's becoming less negative and getting closer to stopping. And you can see how the motion diagram represents here. So here's at A, it's moving to the right, it's behind the origin because there's the origin right here, but you're below here. But then when you get to B, you're at the origin, but you're going really fast. And then when you're at C, you stop and you're furthest away from the origin. And then now D, you're going back towards the origin, you got negative velocity, and then E, you're going smaller velocity right here. It looks like you're going to come to a halt at the origin. So to recap, when you take the slope of a position time graph, you always get velocity. If you take the slope between 2 points, or what we call the chord, then you're getting the average velocity. And if you look at this graph, if you were to take the slope of a line that only touches the curve at one point, then you have found the instantaneous velocity, the slope or the velocity at that specific instant time.